Okay, so now that we have a fundamental understanding of what hydraulics are like and all the different parts and pieces and components, it's going to help us a lot understand braking systems. Now, braking systems are fundamentally similar across all aircraft. They all do the same things and they all use the same physics to do the same things. However, whenever the aircraft start getting bigger and bigger and bigger, and the numbers start getting bigger and bigger and bigger in terms of the weight that it has to stop, the distance it has to stop in, and all those little nuances and complexities, all of a sudden the components and the architecture of the brake system changes a lot along with it. So now that we have that fundamental understanding of hydraulics, what we're going to do is we're going to talk about just brake actuating systems and what does a brake system look like and how is it employed on an aircraft, right? Then we're going to start to build on that information, and we'll eventually culminate with looking at anti-skid systems on a 737 MAX and how they work and why they work. Okay, so we're going to just start by going through the different types of brakes. Now, the one that you're looking at right here is the floating disc brake. It's very common in GA, very common in the corporate world to have this sort of setup. All right, so the 8083 says the caliper straddles the disc. It has 3 cylinders bored through the housing, but on other brakes, this number will vary. I'll tell you that most of your like Cessna 182s, your Piper Cherokees and stuff, they only have one caliper. They won't have the full 3. Usually the 3 you'll end up getting in the bigger, more complex aircraft. Okay, so each cylinder accepts the actuating piston assembly comprised mainly of a piston, a return spring, and an automatic adjusting pin. Each brake assembly has 6 brake linings or pucks. 3 are located on the ends of the piston, which are on the outboard side of the caliper. They are designed to move in and out with the pistons and apply pressure to the outboard side of the disc. 3 more linings are located on the opposite side of these pucks, and on the inboard side of the caliper, these linings are stationary. Now, I'll tell you that construct of having stationary brake shoes, brake disc, brake linings, all kind of the same thing is very, very common. So on one side they will always be fixed, and then on the other side you'll have the piston that will come out, press on the brake pad, and then push against the rotor, which will then effectively pinch the rotor against the stationary brake pad on the other side, causing the aircraft to come to a grinding halt. And that's how the floating disc brakes are arranged. Okay, so this is what a floating disc brake is going to look like. If you'll notice, there you have a brake disc, and then you have lining pucks on this particular type that the piston pushes out of the housing and then onto the brake disc to slow everything down. Now, other objects that are kind of worth pointing out is that you'll have a bleed valves and the fluid inlet bushings and gaskets and all that kind of stuff that's conducive to that hydraulic fluid coming in and coming out of the brake housing. That as the brake fluid pressure increases, or the hydraulic fluid pressure increases, that's just what pushes the cylinder head out against the lining plug onto the brake disc to cause the aircraft to come to a stop. Pretty simple, basically exactly like you have on your car or just about any other type of brake system. Even a bicycle. The bicycle doesn't have hydraulic brakes; it has cable tension setups, but it's very, very similar. If you look at the little caliper on a bicycle brake, you'll have one that's stationary, it's a part of the fixed thing, and then you'll have one that swings in and out based on if you squeeze the brake handle or not. This is basically the same kind of setup, except for instead of squeezing a brake handle and it pulling the brake caliper in, you have a hydraulic system that puts extra pressure on that brake housing, pushing the cylinder head out and pushing against the brake disc. And then to get it back, you have a return spring that pulls that cylinder back in. So you have to match the return spring with the cylinder. So one of the things to look for when you have like a dragging brake, if you're driving around or taxiing around, and you hear that of a brake dragging, a lot of times that spring is off, or it hasn't or it's gotten stretched out or what have you. But yeah, so it looks like there's a lot going on there. This is actually a very, very, very simple type of machine. Okay, here's a cross section of what that would look like. You can see what I want you to focus on is the return spring because that's a part that often gets overlooked in brake construction. A lot of people will focus on the hydraulics, they'll focus on the calipers, but they forget that that return spring is extremely important in order to get it to the caliper, the puck, the lining, whatever your nomenclature you prefer, to pull back so that way the brakes can be either on or off. That is a critical component of the whole floating disc brake construct. Okay, so another real common setup is a fixed disc brake, which is best represented by the Cleveland brakes that you'll find on, say, like a Piper Cherokee or a Cessna 172, things like that. What this does is that on the wheel itself is the brake disc. Now, you'll also have two, like alignment pins that the brake shoe will sit on, and then the caliper presses that shoe into the brake disc, causing it to stop. Here's the an example of a Cleveland brake that came off of a Piper Cherokee. If you notice in the top right-hand corner, that's your brake housing assembly. The caliper or the piston sits on the bottom right-hand side, and then you have two sets of brake linings, brake shoes, brake disc, like whatever your nomenclature, your preferred nomenclature is for this. For this in particular situation, they're going to be referred to as linings. That caliper will receive hydraulic pressure from the brake line. It will then push that caliper out and then onto the top left-hand brake lining that slides up and down those pins there, and then it presses up against the brake disc that's attached to the wheel, and then on the other side it'll cause it to push up against the other side of the brake lining. Basically, think about like if you had like a bicycle tire that's spinning and you grabbed it really fast, and it would cause it to like snap, stopped. That's exactly what the brake would do. Okay, so this is an exploded view of a dual piston Cleveland brake assembly. So same thing as we just looked at, except for instead of having one piston, it has two. Notice that there's a pressure plate that pushes on the brake linings. Those brake linings, another thing to note, they're riveted. So if you're going to change the brake pads on a Cleveland brake system, what you do is you drill out those rivets, and those pads will come out in your hand, and then you put new pads on there, and there are squeeze rivets that get squeezed down on top of them. Now, there are special brake pad rivet squeezers that you can get, but you can also just use a regular rivet squeezer if you have the right dies for it. Anyways, they squeeze on and onto the pressure plate. Then those linings push up against the brake plate and cause the aircraft to stop. Now the anchor bolts or the pins that will allow all this to slide up and down mount into the torque plate, and then the actual cylinder assembly or the brake caliper housing is tied on so that way it can't to fall off with a series of bolts. Now, the clear advantage of this system is that it allows you to take the brakes off without having to remove the wheel. Now, this is really handy, especially if you're working in like the general aviation world, because you don't have to jack the airplane or anything to change the brakes or to service them or to troubleshoot them or fix them. You simply just brake torque on two different bolts that are typically safetied, and then you'll take those bolts out. The brake caliper will slide off and up off of the rotor, and then you can do whatever maintenance that you need to those brake pads or the pistons or what have you, and then you just do it all in reverse, and then all that's left for you to do is to bleed the brakes, which we'll show you how to do here at the hangar. Pretty simple system, very versatile, very widely used in general aviation. Okay, stepping up a little bit in the complexity is dual disc brakes. Now, these get used whenever one single braking disc doesn't supply enough friction. So, kind of basic physics on brakes is that everything will have a coefficient of friction, meaning that there's an equation you can do that says that the amount of force applied to the amount of area multiplied by the coefficient of friction for that substance will result in so much friction, which is then translated into stopping power. And so you can do a pretty easy balance of the equation that, like, if there's so much friction is applied and then there's so much force on the other side, it can only go for so long till eventually it depletes that amount of force. So when we understand that kind of basic math, that basic kind of engineering approach, then we know that having more surface area will increase that equation, increase the friction, and will allow the aircraft to stop sooner. So if you think that, like, you're going to touch down at, say, like a my plane, we're going to touch down at about 80 miles an hour. The plane weighs, if I remember right, about 1,600 pounds or so. And so you have 1,600 pounds traveling at 80 miles an hour, and it's not getting any faster. You have the friction of the wheels on the ground with no brakes applied, and not assuming any sort of aerodynamic braking is being applied. That aircraft will just keep on rolling for an extended period of time. But if we apply a certain amount of braking, it'll stop sooner. Well, if we have multiple disc inside of that same brake housing, then you're effectively going. You're going to apply that much more force to it, so you'll be able to stop even sooner. Now, generally speaking, on like Piper Cherokees and Cessna 185s and things like that, you're not going to turn around and see multiple disc brakes. There's just like not really any need for them. They already stop pretty well to begin with. You don't necessarily need to enhance that at all. Where you'll start to see these start showing up is that the faster the airplane is, the heavier the airplane is, the more there's need for really substantive brakings. Now, especially whenever you start looking at, like, say, corporate jets that have to routinely fly into shorter strips. So let's say, like, I have a business jet and I'm going to go see my client in like Nowheresville, Missouri. All right, so I'm gonna fly up to Nowheresville, Missouri, and because it's Nowheresville and there's nobody that lives there, just my client. It has a small runway, small airport. Well, I'm used to taking off from DFW that has like just like unlimited runway length at most places, and so whenever I go to land, I'm going to have to really be really cautious that I land at the very front end of that runway, and that I apply the brakes correctly so I can stop and not run off the end of the runway. Well, having multiple discs in my brakes allow me to stop that much sooner. So if I really need to stop like really fast, I can get on the brakes and just stand on them, and it'll stop inside of that short runway up in Nowhereville. So not saying anything against people in Missouri. I'm sure it's fine, just as an example. But that's the purpose of having multiple brake discs. You notice that the buildup is a little bit more not complicated, but just busier because you have more parts and pieces. You have self-adjusting pins, brake linings, the disc, and then you have a center carrier, which is really kind of the biggest change to all of it. That you have your actual housing assembly and your housing back plate, but in the middle there is a center carrier that also is kind of a part of the whole braking system. So that's something that is a new addition for us, but not really that much more cognitively taxing. They're pretty simple machines at the end of the day. Okay, so runway length and speed are only two components that might lead you to need more aggressive brakes. The other thing that you might need might need to take into consideration is the weight of the aircraft. Now, a multiple disc brake system is very common in older airplanes, and the reason is that like the older transport category aircraft generally are very, very heavy. And so since they're very, very heavy, they need multiple discs, just like we saw, an additional disc being added on. This category aircraft was going to need multiple discs to get that friction to where we need it to be in order to stop in the runways they go into. Now, you wouldn't think that too much about these, but these are the type of things that limit what aircraft can go into what airport. So if they can't stop in the length of runway that's prohibited with a decent safety margin, they won't go in there. That might limit an entire company to get there. And if there's a certain type of good that's delivered by that very specific company or type of companies that they're all similar to each other, what will end up happening is that good just won't be available in that area. And so you can see how like such a small thing may affect the greater market. Just simply because somebody decided to not install a modern braking system on an aircraft. Maybe they used one of these older multiple disc brake get-ups. However, that is not the most modern type of disc brake. Let's talk about the segmented rotor disc brakes. Okay, so a segmented rotor disc brake allows for heat to dissipate a lot easier, uh, just because they generate so much heat whenever you're applying the brakes that really becomes kind of detrimental. Having a segmented rotor disc allows you to use stator plates up against the rotor assemblies that only really contact very specific parts. That allows for airflow to fly around and actually cool the brakes off. Now, if just like in cars, like if the brakes get too hot, you could suffer from brake fade, and that is not a good situation to be in. It's gotten so hot that the brakes don't produce enough friction to stop the car anymore, or stop in this case the airplane, and could slide all around and be very, very dangerous. Okay, so carbon brakes is something that you'll also encounter out there in the field. Carbon brakes came around as a way to reduce the weight of those brake pads and stators and all that good stuff. These have kind of taken the heavy commercial industry, I wouldn't say by storm, but over the years they've slowly been replaced and set up. Now their main advantage is that they're about 40% lighter than your typical brakes. So for one, like simply moving them around doing maintenance on them is a lot easier. Number two, and probably the most important piece is they don't come at such a high fuel cost. So you have to haul around, your, like nearly twice the weight of just brakes just to get off the ground. So you imagine how much money that saves, especially whenever you're doing long haul flights back to back to back. That actually is a pretty substantial savings for them. Now, the flip side of it is they're currently very costly to make, but over time this will go down. Now, these brakes effectively are the same type of material that like the belly of the space shuttle was made of, or the plates on Starship, so that way it can take the frictional heat and dissipate it rapidly. So that way the brakes are more effective, they wear less, and all that. But yeah, so you'll probably encounter carbon brakes out there somewhere in the field. Okay, now that we understand hydraulics and we understand the different types of brake assemblies that we could have, let's talk about the actual actuating systems that make the brakes work. Now, there are three fundamental different types. There are independent, booster brakes, and then hydraulic system brakes that are all tied together. So let's start off with understanding the most simple and straightforward one, and also probably honestly the most common one in terms of just sheer numbers, is independent brake systems. Okay, so independent braking systems are probably the most common that are going to be found on Cessnas, Pipers, all your old GA aircraft, your RV-12s, all the RV series, because they are fundamentally simple. They're very, very basic hydraulic systems that all you're effectively employing is a master cylinder and a slave cylinder. So the master cylinders in this type of braking system is generally almost always directly tied to the brake pedals. The brake pedals have to move in a long distance, which then compresses the master cylinder, which then compresses the fluid inside of the brake lines and pushes out on the slave cylinders, which we also know as the brake calipers or brake piston or brake system pistons that push on the brake lining or brake pads against a rotor that slows the wheel down from turning. Really, really simple. They also generally will have a parking brake, which allows you to lock the pressure into the cylinders or into the brake cylinders that hold the wheels and keep them from moving. Nothing really big, nothing really complex. Okay, so this is a master cylinder off of one of those systems. Notice that it's really simple. It's just simply a little kind of actuating cylinder. Nothing really over the top. Now, another thing to take away is look at the travel that bell crank has in and out of the cylinder. When you look at that compared to the distance the brake pad has to travel, which is probably about a quarter of an inch. It's not really that much at all. You can start to see the sacrifice that you have to make in the travel in the master cylinder to the actual travel that you get on the slave cylinder downstream. That sacrifice allows the mechanical advantage to take place. You also want to look at the differences in the cylinder size. Now, that master cylinder's not very big on the inside, but the actual brake cylinder in the housing is probably about 2.5 inches in diameter. It's fairly substantive, and then when you apply that to the brake pad, the surface area of the brake actually gets a lot bigger, thus giving you the braking power that you need to stop a small 1,500 pound or 2,000 pound aircraft. But you can see where you'll start to run into problems once the jet gets heavier, or you have to stop it from traveling much faster across the ground. Because keep in mind that a touchdown speed for like a Cessna 172 can be in the 50s and 60 mile an hour range. On the Piper Cherokee, it's about 80 miles an hour. But when you get up to say your Phenom 500, the touchdown speed is going to be well over 100 some odd miles an hour, and it's going to weigh a lot more. So you're going to need a lot more braking power to stop it. So where the independent braking system shines is on simple light aircraft, but where it fails is in terms of braking power. You could employ a system like this on let's say a 737, but you better have several miles worth of runway to get it to stop, because when you have that amount of weight touching down at that speed, an independent braking system like this is just not going to cut it. Okay, so the next type of brake actuating system are going to be boosted brakes. Now these are actually pretty cool. They still use hydraulic pressure to get the actual boost, but what it does is it augments the brake power that the pilot is actually applying. Now the way they do this is through that little spool valve that you're looking at the very top of the cylinder, and this is a boosted brake cylinder cutaway that you can see. Now, what happens is that in the whereas an independent brake system, it's totally reliant on the amount of force and pressure that the pilot can apply to the into the master cylinder. Now, and then the mechanical advantage of the system multiplies that power by a set amount. This uses that same sort of physics. However, whenever the pilot applies a certain amount of brake pressure, the spool valve allows the pressure manifold, or the manifold pressure of the hydraulics to come in and then pressurize the rest of that fluid, so that way you get an outsized amount of input pressure into the brake system. So effectively, as you be taxiing around, you can hit your toe brakes, and it works just like an independent brake system. And let's say you're going to land, and you really need a lot of extra oomph to get that aircraft started, you can press just a little bit further. It opens that spool valve. You get a lot of extra pressure pushing down on the brake cylinder, and it will help the aircraft come to a complete stop. This one's a little bit more rare, I'd say. Most of them just use hydraulic pressure for brakes, and you kind of bypass this whole thing, but you could encounter it. Okay, so the most common type of braking architecture that you're going to come across in heavy commercial aviation are power brakes. Now, this graphic out of the 8083 will allow us to kind of just talk through what that will generally look like before we kind of move on. So, looking at item number B, we have hydraulic system pressure coming into the brake system. So that's one of the kind of key differences between boosted brakes and independent brakes in a power brake system. Is the power brake system looks at the brake system as just another wing of the hydraulic system, as opposed to being a completely independent system. So if you have hydraulic problems in one place, there's a good chance you might have hydraulic problems manifest somewhere else. Now, that check valve there helps some of that, but at the end of the day, they're all still connected. And even with shuttle valves and check valves and all the other types of selector valves that you may have, that will still be the case from time to time. Now, once we're through the brake check valve, we get to the accumulator. So remember, an accumulator allows for instantaneous hydraulic pressure to be available whenever needed, and it helps also to develop hydraulic pressure and recover it much more quickly than a pump will. Now, there's still pumps that move the fluid and stuff, but the brake accumulator uses bleed air to help pressurize it to a high degree. Now, the blue on there represents the air side. The red is the actual hydraulic fluid side. So following down, we'll get to the power brake control valves. Now those are valves that basically make the decision of like how much pressure gets applied to the actual brake assemblies, and then based on the control inputs coming from the cockpit. So if you have a full braking pressure in the cockpit, well, then those valves will be open wide. If it's just a little bit, then they'll open just a little bit. Very, very simple kind of construct, but what very important consequences in the way the amount in terms of brakes that get applied. The anti-skid control valves are right there. We're going to just skip over that for right now because we're going to get into anti-skid here in a little bit. But then it goes on down to shuttle valves. Remember, shuttle valves will allow for pressure to come one way, or in the event of emergency, it'll allow pressure to come from somewhere else. So that's what they're there for. You have the brake assemblies themselves. So on, like say, a 737, you're gonna have some pretty advanced brake packs that go on there. And we'll get into that here in just a little bit. What is actually on a 737 Max, and then on the other side is that you have accumulator air pressure. So the shuttle valve can essentially say like, "Hey, look, hydraulic systems have failed, and so we're going to turn around and we're going to take emergency bleed air, and we're going to use it to help stop the brakes, so that way the plane doesn't go cartwheeling out of control." But that's basically how a power brake system will work on a heavy commercial aircraft. They're all going to look very, very different. Airbus uses 3 independent hydraulic systems plus the RAT, and they're all intermingled and mixed, which in my opinion is probably actually superior. That their hydraulic system, while is more complicated and can lead to more problems, is probably more redundant. But essentially, they all kind of follow this same sort of sequence of events, with slight deviations. Now, if we look at the top, we have cable brake systems that control your valves as opposed to like electronically. Then there's a couple of other things that I want to try to bring to your attention that we covered in hydraulics that have now come to find their place in the braking system. Primarily like the shuttle valve, like we just talked about, and the fuse. There's a hydraulic fuse on the top right hand side. So if you go back and remember what fuses are, if you've forgotten it already, that's a place that you could potentially find a hydraulic fuse. You also have a auto brake pressure control system that's right there. So it's simply monitoring the amount of pressure that's applied from the cockpit. Generally tries to apply the same auto pressure or the same brake pressure that the pilots is wanting to input, but make sure that it's evenly distributed. There's no spikes or anything that's wonky. Keep in mind that you can steer the plane with differential braking, and so you want to make sure that the brakes are applied uniformly to both sides unless otherwise commanded. So let's say if you have brakes being applied in the cockpit at like 100%, we want to stop, but there's a disproportion, or there's 50 psi on one side and 100 psi on the other side, then that plane's going to want to make a hard like left hand turn, because one side is going way faster than the other side at that point. And so those types of systems are there to make sure that doesn't happen. But that's a kind of a real high level overview of a power brake system. Okay, and to that end, the 737 uses this device called a brake metering valve to make sure that all of the brakes get the appropriate pressure. Now, this is a used part, but it's being sold for $5,500. You can see how expensive and how complicated some of these heavy commercial brake systems can actually get. Now, here's a cutaway. Okay, here's a cutaway with kind of a sequence of how a brake metering valve makes sure that all of the brakes need to get the pressure that they actually are entitled to for proper operation. So a machine slide or spool moves laterally to admit the correct amount of hydraulic fluid system to the brakes. The pressure developed is in proportion to the amount of the rudder brake pedal is depressed and the amount of the slide is displaced. The slide spool also simultaneously controls the return of fluid to the hydraulic system return manifold when brake pressure is released. And so that's how they manage to manage such a complicated brake architecture. Okay, so this is the 737 MAX braking system architecture. We're going to follow the normal system B pressure, and then just let it flow through the rest of the system, and we're going to talk about the components and all the little parts and pieces as it goes. So it starts off with hydraulic pressure being charged from the accumulator, as well as just from the regular hydraulic system. So you have like the hydraulic system that's pressurizing the system, and then you have a brake accumulator that's also sitting there ready to back it up if need be. And there's two check valves there that allow the pressure to flow into the brake system, but not turn around and go back up without having to at least encounter the accumulator isolation valve or one of those two check valves. It then flows down into the auto brake pressure module, the normal brake metering valve on both sides. So that auto brake pressure module, we'll get to that a little bit more when we start talking about like anti-skid and some other systems that intertwine with that. But then you have the normal brake metering valve that on the right side allows the system B to return at that point. So if there is an excess of pressure, or excessive fluid, or it's just simply being pressed back up by the return springs, it'll go up into the system B return right there. It goes down to then the auto brake shuttle valves. So remember, a shuttle valve allows pressure to come from one or two different directions. So at that point, they're going to select where the brake pressure comes from based on what basically the auto brake system tells it to do. It will then flow down into the actual main, so the left and right wheel brakes. And note that there's not any nose gear braking. That's common on pretty much all aircraft. I've never seen a nose gear braking system. Not to say it's not out there in some rando model, but I'll tell you for a 737 and all your other heavy commercial stuff, the nose gear is there to support and to steer, not to brake. All right, so what does the actual braking system look like on the landing gear itself? You have a normal anti-skid valve, so we'll talk about anti-skid here in just a little bit, and that'll make a little bit more sense. You have a hydraulic fuse as well, so if it overpressurizes, that fuse will do its job and make sure that the rest of the system doesn't get overpressurized. And then you have a shuttle valve that basically allows, hey, look, are we going to take pressure from system A or system B at that point? And then it goes directly into actuating the actual brake pads themselves. Now, what I want you to kind of understand is that like if you look at just like the left wheel brakes, right wheel brakes, you have the tire, and then you have like a good solid system B pressure line going into it. What's interesting about that is that if you think about it, it's not really that different than the independent braking systems that we saw, like the Cessna 182 or a 172 Piper Cherokee, all that good stuff that we looked at just a few minutes ago. They're effectively the systems are the same. Where this one differs drastically is just that all the stuff that is in between. So like on a 737 you still have your toe brakes, and that's going to actuate the movement of hydraulic fluid and pressure onto the brake pads to just cause it to squeeze. Now to squeeze up against the wheel causes it to stop. Now I bring that up to say, like, don't let this stuff intimidate you. It looks like a big just mess of all these different lines and all these different modules and things like that. A lot of this is not, it's not really that bad. If you end up having to work on something like this, or troubleshoot it, every one of these components, there's going to be a task for, hey, remove and install. It's going to tell you, hey, look, shut this off, do this, do that. Make sure here's the caution warnings and notes. You just follow the directions, and you're good to go on whatever it is that you need to do. It's not as bad as it seems. Just looking at the picture here. Now, the notice the system B return also flows out of the of a various system of valves. You also see that there's an alternate system A pressure that ties in as well. So notice the redundancy, and that's going to be common with just about every single system that is tied to the hydraulic system. That every one of them is going to back up the other one, so that way if there's a failure somewhere, we can leverage what we have on board to get the aircraft on the ground. But yeah. Okay, one of the last components is brake deboosters. So some aircraft brake assemblies that operate on aircraft hydraulic system pressures are not designed for such high pressure. So the hydraulic system generates more pressure than the brake assemblies can take. So they provide a debooster provides effective braking power through the brake system, but require less than the maximum hydraulic system pressure. To supply the lower pressure, a brake debooster cylinder is installed downstream of the control valve and the anti-skid valve. The debooster reduces some pressure from the control valve to within the working range of the brake assembly. So effectively, what's happened is you have hydraulic pressure that's coming in, and the debooster just allows that pressure to bleed off, so that way it can get to the right pressure for the brake assemblies themselves. If not, you would overpressurize the brake assemblies, and they would just effectively blow up. So you'll see these a lot on the front of the struts of your different aircraft. It'll look like a big white cylinder on top of there, but that's what they are. So those deboosters, all they're really doing is just kind of a pressure reducer, is the best way to think about it, on board the aircraft. Okay, now that we understand hydraulics and brakes and the architecture of a braking system, let's talk about what do we do to maintain that braking system. What does servicing brakes look like? What does inspecting brakes look like? What are the things that are we looking for whenever we have to do maintenance on the brake system of whatever jet that we're assigned? Okay, so the first thing we're going to look for whenever we are servicing and maintaining and inspecting brakes is just where's our brake lining at? The brake pads, brake shoes, whatever, like your preferred terminology in aircraft, are usually going to be called linings. They wear, and that's by design. Now, the reason why it wears is that over time, or like as you use the brakes, heat has to be generated, and something has to give. You can't just continually just smash two things together and expect them not to break and not to give way. So the manufacturers of the brakes have decided to make kind of a tactical decision to put brake pads on the brakes itself, so that way they slowly will wear out over time. Now, given that being the case, the aircraft manufacturer gives specifications for lining wear in its maintenance information, meaning that every so often, either the brake pad has to be changed per, like, say, hours or calendar months or whatever, or on condition, meaning that, like, you're going to say, like, hey, look, like on my plane, the brakes have to be serviced every 500 hours. Part of the brake service is changing out the pads, unless you do a check on the brakes, like during an annual, and say, hey, look, the brake lining is not thick enough, and so now we need to change it. Now, on general aviation aircraft, lightweight airplanes. This is it's still very very important. And can be a safety concern, but it's not near the level of concern it is with like heavier aircraft that travel a lot faster. If the brakes goes out on a private jet when it lands, you have a $40 million missile going down the runway that you can't stop or do much about. You just do aerodynamic braking and then pray for the best and hope you have a long enough runway. So this is something that you want to pay attention to, and you don't want to just take for granted and kind of like hand wave, like, oh, it's just brake pads or whatever. These are things that are really important. Okay, so the lining wear that we're going to measure is going to be measured in between the disc and the housing. So that little gap there is what we're going to measure. It's not, and that's only whenever it's not measured via a wear pin. Sometimes you'll have a little pin in there that'll tell you where the brakes are at. If it's super flush up against the housing, you know that the brakes are worn out. It's time to change it. And if it's sticking way out, then you know the brakes are brand new. Okay, so the distance between the disc and the portion of the brake housing is when the brakes are applied, which is important. The brakes have to be applied. It cannot be you know, just sitting static or whatever else, because at that point the system's relaxed and you're not really getting a good picture of where that lining thickness is. Now each manufacturer of brakes are going to tell you how much brake pad is allowable, and every aircraft maintenance manual will largely repeat that information. However, Cleveland brakes almost always can be measured by using a number 40 drill. Now, you simply can take the drill and just lay it in between the gap between the disc and the housing, and as long as there's plenty of play in between either side of the drill, then you know that there's plenty of brake lining left. If it gets to the point where you apply the brakes and you can't fit a number 40 drill bit in between the two, then you know it's time to replace it. You can do the same thing with a leaf gauge. You simply just feather it out to 0.098, stick it in there. If it fits, then the brakes are good. If it doesn't fit, the brakes are bad. It's pretty simple. But no matter what, like this is just an example. Always follow whatever the manufacturer recommends to for measuring the status of the brake linings. Okay, the next big inspection criteria you're going to look for is just by simply pushing on the brakes and see if it has a spongy or soft feel. If it does, it means that there's air somewhere in the line. The brakes should feel hard, because keep in mind you're pushing pressurized fluid through those lines. If they feel soft, the only thing that means or the only thing that will compress inside of those lines is air. If it's full of fluid, it won't compress at all, and it'll feel like you're pushing on something, because it's just very much like if you had like a push pin that you're pushing on, like a rod or whatever, except for this time it's all made out of fluid. So if air gets in there and it starts to compress and starts to feel soft, you know you have a problem. Now, this is a method of bleeding the brakes. And bleeding basically means that you're going to like pull the fluid out with the air, and you're going to replace that air with fluid all the way in the lines. So that means that like typically the way I've seen it done, the way I've always done it, is you would press on the brake pedals. You'd have somebody up in the cockpit working it back and forth, back and forth, back and forth, and you crack there's a little zert fitting on there that you'll crack, and it'll let the air out. Once you get a steady stream of brake fluid out there, you turn it real quick, and that basically seals up that line. All the air has come out, and all that's left inside of the line is just charged brake fluid or hydraulic fluid, in our case 5606. And then you'll service the reservoir, make sure that all of the brake fluid is topped off where it's supposed to be, and then you have a fully healthy system. Okay, here's another technique. It's called the bottom up method. You're going to take a bleeder pot and you're going to attach it to that fitting that sits on the brake housing, and you're going to pressurize that fitting. You'll crack it open. It will then push hydraulic fluid all the way through the lines, and then it'll push the air out of it into the brake reservoir, and it'll bubble to the top. Once you have a good steady stream coming out with no air bubbles in there, out of the brake reservoir and into a catching container of some variety, then you know that the brakes are fully serviced. Then you'll simply cut the pressure pod off, close the zert fitting, and you're good to go. And then at that point, you're ready to use the brakes. In either case, you should always MOC them while they're on the ground. So do a maintenance operational check, step on the brakes, make sure they're hard, and then whenever you actually go to return the aircraft back to the customer, you're going to go through all of the checks that at the end of the annual or whatever service you're doing. You should always crank it up, taxi it forward, step on the brakes, make sure the brakes work fully. Because what you don't want to do is return the aircraft back to the customer with faulty brakes, and then it would be an unprofessional look on you, but also could be very unsafe if it's not caught in time. Okay, so now if we decide we're going to bleed the brakes on, like say, a 737 or anything that has a power brake system, you're going to end up having to use a mule. You can't bleed them out from pressurizing from the top. What you'll do is you'll simply attach the mule to the aircraft, start working the hydraulics, and you'll effectively crack the line farther down to let all the air escape, and then once you start seeing a production of hydraulic fluid, you'll close it off. And of course, if you ever see a aircraft brake leaking, it's time to figure out what's going on with it. You need to basically clean everything up first, and then start pumping the brakes to see if you can see any squirts of brake fluid anywhere, and then that will kind of start to guide your thinking on how you need to fix it. Ensure that there's proper bolt torque on everything, proper torque on all your lines and fittings, and there should be torque stripe applied to everything so that way you can see if it broke or fell off. I worked a deal recently where this exact scenario had happened, except for on a citation. What was going on is that they had flown into a cold area. The O-rings had shrunk, and then whenever they got back down to Texas, it got warm again, and then they expanded back out. Well, that change in temperature caused the O-ring to crack, and then whenever they started to apply the brake pressure, the fluid started to slowly seep out of the line. So, something to look out for. Okay, so aircraft brake disc. Once you get them pulled off, you're going to want to make sure that you've inspected them mainly for cracks, but also any kind of gouges, any sort of corrosion. Now, granted, these are iron, and they're going to get exposed to heat, and they're going to get exposed to a lot of friction, so you're going to see some oxidation on there. That's fine. Basically, the first time that you touch the brakes whenever you're going down the runway, it's going to take care of most of that corrosion. But really, what you're looking for is things that are going to permanently damage it. And so, like a crack could be one of them that you need to pull the brake disc off the wheel and replace it. Now, this brake disc it goes to Cleveland brakes. They mount directly to the aircraft wheel, and then the brakes set on either side of that disc, and then squeeze it. So brake disc is one of the primary things you're looking at whenever you go to pull brake pads off and inspect it. Now, pulling the brakes, you're also going to be looking at seals. You're going to look for the housing and piston condition. You're looking for cracks and any sort of damage that may have occurred through just wear and tear, and or pieces kicking up and cracking the housing, or scratching it or otherwise damaging it in some kind of adverse fashion. You're also looking at there behind every one of those pistons is typically you'll have at least an O-ring, if not an O-ring, and then another white pressure ring that goes behind it, just depending on the model of brakes. Those will go bad over time, and you'll have to pull them out and replace them. Not really that big of a deal, not that hard, not that expensive to replace, but just something you have to keep an eye on. So that's something you're also looking for it. All right, so let's go over a couple of common brake failures or malfunctions, and then we'll go on to anti-skid. Okay, so these are the three most common brake failures that you'll have. It's overheating, dragging, and chattering and or squealing. Overheating is real simple. Somebody's just on their brakes too much. Their touchdown speed is too fast, or that's basically it. If they are the type of person that doesn't keep their heels on the floor whenever they're taxiing around, and they keep their whole foot on the brake, they're more likely to every time that they push a rudder input, they push on the brakes, and it causes it to drag. Now that condition will cause the brakes to heat up. And the maintenance manual, or the flight manual rather, is designed to specifically to prevent this sort of problem. They're designed to make sure that your foot doesn't cause the brake to be on too much and then cause it to get too hot. And then once it gets too hot, then as metal heats and expands, it'll also then contract as that heat dissipates. And as it contracts, it can potentially warp, crack, or any number of things. So while overheating doesn't have like this is like a certain symptom, like this is the symptom of an overheated brake, it could cause a whole litany of problems. And so one of the problems that or one of the source or what the root cause analysis that you could do on the brake problems could be the fact that it's being overheated from the way that it's being operated. Dragging, on the other hand, is something that it's internally failed. The whenever the brakes are applied, there should be a return spring that pulls the brake back. And so whenever that doesn't happen, then it'll just drag on the on the disc the entire time. You'll sometimes, if it gets really bad, you'll hear it, and other times like you'll put the power in, you'll notice the plane is just not taxiing as fast as you think it should, and that's because it's dragging. There's a mechanical failure causing the brake lining to constantly be in contact with the disc. And so with that, you'll end up having to pull the brake caliper off, try to figure out what's going on, potentially start replacing some parts. But yeah, so dragging is that. Now chattering, on the other hand, it can come from several different places, but most commonly it's come from a warped disc, which is another kind of byproduct of overheating. So the disc gets overheated because it's being rode too hard for too long. It cools off, and when it cools off, it starts to bend, even ever so slightly. And you'll be able to see that because it'll look like waves on the brake disc. You'll see, hey, look, here it seems to be like really in contact with the brake lining, and here it doesn't. And when you pull the brake lining off, if it looks like it's not wearing evenly, there's something wrong with the brake disc. And so that all of that will cause it to chatter and or squeal whenever you apply the brakes. Now, that being said, the only time I've ever really seen like truly bad brake problems is with the heavy commercial aircraft, because they just get so much more wear and tear put onto them. However, most of those operations are set up so that way they can deal with those types of brake issues pretty easily. Like they simply have modular systems that allow brake changes to happen really fast. They have back shops to rebuild the brakes and put them back on, and they have a pretty robust training program for their pilots, so that way everybody knows what right looks like when it comes to brakes. So with that, let's look at the next thing. All right, finally, the kind of coup de grace of all the conversation around brakes is anti-skid systems. On a 737, you'll go in there and you'll see its own line replaceable unit, its own LRU for anti-skid. What is anti-skid? How does it work? And what do we have to do with it? Okay, so anti-skid systems. So anti-skid systems not only detect wheel skid, so it's sliding around, it also detects when the wheel skid is imminent. So it knows that there's preconditions to a wheel skid, and it's constantly looking for it and then trying to curtail it before it ever gets going. It does this by automatically relieving the pressure of the brake pistons of the wheel in question by momentarily connecting the pressurized brake fluid area to the hydraulic system return line. So basically, it's opening a valve and allowing the pressure to come off of the brake pistons, so that way the wheel can spin and rather than lock up and skid. So maximum braking efficiency exists when the wheels are decelerating at a maximum rate, but not skidding. So there's a if you want to use a calculus word, you're looking for an asymptote. There's an asymptote that where there's this break point between a sliding, skidding wheel and a maximum decelerating wheel, and we're trying to find that nice little equilibrium right there before at the border, and that's what the anti-skid system does. So to ensure that this does not lock up and cause a skid, each wheel is monitored for the deceleration rate faster than a preset rate. So we know that anything beyond this level, north of the asymptote, is going to be a skid. Anything below it is an inefficient deceleration rate, and so we're trying to find right there at that level. And they note that's a number that can be known and can be calculated on the fly, and then a percentage below that is where the anti-skid system wants the aircraft to live. Now, there's a various designs of the anti-skid systems. Most contain three types of components: wheel speed sensors, anti-skids, control valves, and a control unit. What you're looking at right now is the 737's anti-skid panel that's on board, and the auto brake. So auto brake is basically we'll go over that in just real quick, but essentially it's whenever the aircraft lands. Weight on gear comes on, and it knows, hey, look, we need to start applying the brakes, so it does it automatically, and you have the anti-skid locked on in case there's certain conditions present that could cause a skid. So the airplane is actively looking for a skid while it auto brakes itself at the right time at the right rate. Okay, so the first component of the anti-skid system we're going to look at is the wheel speed sensor. They may be alternating current or direct current, so AC or DC. It can be either or. Their typical AC wheel speed sensor has a stator mounted in the wheel axle and a coil around it that is connected to controlled DC source, so that when energized, the stator becomes an electromagnet. Rotor hub that turns inside the stator is connected to the rotating wheel hub assembly through the drive coupling, so that it rotates at the speed of the wheel. Lobes on the rotor and the stator cause the distance between the two components to constantly change during rotation. This alters the magnetic coupling or reluctance between rotor and stator, and as the electromagnetic field changes, a variable frequency AC is induced in the stator coil. So basically, you have kind of like a mini like electrical component down there, or a mini electrical generator, that as the wheel speeds, there's a voltage output. And it says, like, hey, look, we know that at this RPM of the wheel, given these conditions, we produce this amount of voltage at this frequency, so on and so forth. And so that allows the airplane to know how fast that tire is turning based on the electrical output. Really, really cool, ingenious way to employ electronics into the system. Okay, the next piece of the pie is going to be the control unit, or the LRU, the anti-skid control unit that sits in the eBay. Basically, this is the brains of the operation. Everything you see that's happening up top with the control panel basically talks directly to this box, and the skid wheel, or the wheel sensors, will be piped into this LRU, and we'll look at the hierarchy of how it talks to each other. But essentially, this box is looking at the speed in which those wheels are turning. It's programmed to say, hey, look, at certain circumstances, we're going to leverage the control valves and let some pressure off to prevent a skid. So it's nested into that the wheel speed sensors, and as well as the electronic controls for the hydraulic system, so that way it can command certain valves when need be. Okay, so this is an anti-skid control valve. Essentially, it does exactly what its name says. That whenever the anti-skid control unit says, "Hey, look, we have a skid coming up. We need to do something," these are the valves that relieve the pressure or close whenever the situation has abated, and allows the anti-skid system to work. Now, these will tie directly into the other brake lines, and or the brake system, and be just a part of it. For the most part, they don't do anything. They basically stay in their fixed position, and only ever really they only ever really actuate under very strict conditions. So typically, the part that goes bad with an anti-skid system is going to be your wheels, because they're down there with the muck and the grime, and they also are electric, and so, like, being down there in those types of conditions is generally not the best thing. They also have the most kinetic use, so they spin the most. They actually move. The LRU, I have seen anti-skid systems LRUs go bad. It's definitely not not super normal, but it does happen just like any other LRU out there. So these you don't really have to worry about as much. The wheel sensors typically are going to be the bad thing, and the auto test, the bite test on the box will usually tell you what that is. On a 737 Max, however, maintenance data pages will also tell you that as well. Okay, so here's the hierarchy for or the architecture for an anti-skid system on a 737. If you'll notice that the left brakes and the right brakes all pipe directly into the control unit. The control unit, on the other hand, also takes inputs from the alternate brake switch. Now, from there, once it takes all that, those are the data points coming into it, and the outputs are going to be the left and right inboard and outboard anti-skid valves, and that's really all there is to it. It also has alternate valves on the left and the right side that could be bad. Now, other control inputs. So we'll pause with that. If you have a problem with your anti-skid system, know that one of the ways that best to do systems troubleshooting is just simply know the system. If it know you know what information it's getting from where, and you know what information that LRU is pushing back out, you can start to kind of like figure out where the breakdown is in communication along that pathway. Now, this one is just like everything else. The Ataroos, the PSEU also talk to that box. So you could have bad Ataroo problems or bad PSEU problems that are feeding into the anti-skid. So if you turn around and you get an anti-skid fail, one of the things to look for is maybe also check and see if the Ataroos are healthy and the PSEU is healthy. Generally speaking, if you have a failure of an Ataroo, it's going to affect a lot of different things, and it's going to all point to the Ataroo. If you have a failure of the PSEU panel, then it'll also point to a whole host of other things as well. And so you won't know necessarily have to do that. However, there are situations where you could have like a problem with one discrete, that one discrete seems to only talk to the anti-skid, and that could be actually the problem. The anti-skid situation is fine. So one of the quickest ways to fix this is simply just by hot swapping Ataroos. You can just pull one out of the rack and swap them around and see if the problem follows. If it does, then you know you have a bad Ataroo, and you need to start working that route rather than immediately going into the anti-skid system.